Hi, linear algebra students. So in this video, this is a follow-up of the last video. So if you haven't seen the last video, which explains the setup of that problem, the distance between skew lines, you should watch it, okay? Because what we're gonna do is we're gonna take the recipe that we had in the last video and we're gonna apply it on this particular example. Okay, this video is mandatory to watch. You can certainly have this on your final exam. Okay, we want to find the distance between these two skew lines. Okay, so I'm telling you that they're skew, so you don't have to verify that, but normally you would have, because if you just have two lines, what you need to guarantee that, yeah, they're not skew. Remember that you do this with the scalar triple product of like the vectors q, v1, and v2. But we are given that there's skew lines, so we can apply the process directly, okay? But we have to cook it with the correct ingredients, right? So let's actually label everything. Let's give everything a name. So this will be the position vector P1, and this will be the position vector P2. Okay, so this is our P2. So what this means is that on the stem number 1, the vector q that we're talking about is simply P2 minus P1. So there you go, like P2 minus P1. So obviously, you just take these vectors and subtract them from each other. You're going to get 1 plus 2, so 3. Then negative 1 minus 1, so negative 2. And finally, 2 plus 1, 3. So that's going to give you the vector q that you need in your first step. Okay, so the vector just from one line to the other. Now, again, let's color code the vector v1, which is this guy. And the vector v2 is that guy, right? So this is v2, okay? Remember that we need also the normal vector. So the normal vector is simply the cross product of these. Okay, so the cross product of v1 and v2. Okay, so let's actually write down the formula for the cross product before we go crazy. So it has like 3 determinants. The second one being negative, remember. And we're filling it in with the components that are here. So 2, 3. Whoops, no, this is second and third component. I always mess this up. Like I always want to write the first two. So be careful, don't do my mistake. So it's the last two components, then it's the first and the last, so 2, negative 1, and then finally it's the first two. Yeah, there you go. And of v2, well, you do the same thing, right? It's going to be the 2 last, so in other words, 2 and 4. Then it's going to be first and last, so negative 1, 4. And finally, it's going to be the first 2, so negative 1 and 2. Let's verify one more time that I don't have any mistake. So, okay, this one is going to be the two last, this one first last, and finally we have two first. Okay, we're good. This is the cross product, and we calculate it. So all right, this is 12 plus 2, 14. Okay, how about this? We have 8 plus 1. Okay, so this, okay, be very careful here. 8. And now we have positive 1, but we subtract. So it's going to be 8 minus 1, 7. There you go. But because of the negative here, it's going to be negative 7. Okay? And finally, what do we have here? We have 4 plus 3, 7. Okay? And that is the cross product. But it brings me to give you an additional trick. Okay? Because nothing forces you to take that normal vector, right? you know, for instance, that you can actually scale it out. You can scale a 7 and have like 2, -1, 1. So the scalar multiple is actually not important, right? You can either take this as a normal vector or this as a normal vector. So what we're going to do is we're going to take instead, n to be the vector 2, -1, 1. Okay, we're going to choose our normal vector to be this instead of the cross product. All right, number 3, we project Q on N. So the projection of Q on N. Okay. Can I color code this? Unfortunately, I think I'm running out of colors. Yeah, I'm running out of color, unfortunately. So there's no point really color coding it. But very, very simple. So it's going to be, let's rewrite the formula at the very least, n dot q, because I didn't write it here, divided by n squared times n. And actually, let's do number 4 immediately, because I think it does simplify the calculation. So we're going to get, okay, so number 4, we take the absolute value, the norm of the projection of P dot Q. And you should remember in the last video that this is the absolute value of the dot product over the norm. So in other words, we have only 2 things to calculate. We have the absolute value of the dot product, so n dot q. So n, we have it here, right? It's going to be 2, -1, and 1. And q, we have it there. Okay, so I'm dropping the color code, but don't be confused, right? Q is there. So -2 and finally 3. Grind the coffee. This is 6, 9, plus 2, 11. There you go. And the norm of n, so remember, this is the square root of like all of these squared, right? 2 squared, like -1 squared, and then 1 squared. So again, grinding some coffee here, we have 4, 5, 6. Which means that the distance, we could call it d, is simply 1 over the other, right? 11 over the square root of 6. Little bit crooked, but no worries. All right, I hope this was helpful. So this is the last video actually of the course. Okay, so good luck, study well, and see you another time.